This exercise will deal with the poroelastic response in the Wilmington Oil Field in California. This is the Los Angeles area. Let's see, there's Beverly Hills. You might have heard of that. You can see here it's in Southern California. And the green shapes here are oil fields. They're relatively small features, and they're along these trends here that are defined by the geologic structure. And the largest one of these is the Wilmington oil field shown here. It's this region right here. And there are other oil fields, this Torrance field along strike. So if we look at a little bit of a blow up here, we can see the oil field here. And this is the scale. That total length, there's 16, so it's about 20 kilometers in this direction and say 5 kilometers in that direction. So here's the geology. This is a cross section, northwest to southeast, so cutting through the oil field here. And there's an unconformity right here. And these sediments here, many of them are oil bearing. So the scale, that's 2,000 to 5,000 feet. And many of these formations here have oil in them. So a very thick sequence of oil bearing sands, and there are interbedded finer grain units, but a lot of sandy material. And then above this unconformity, this material here has no oil in it. And you can see here, this is a map of the oil field. And you can see that these things here are offsetting these structural contours, and these are faults. So the oil field is broken up into faults, and where faults cut through sands, often what happens is the faults form a low permeability layer, and these faults then tend to break this oil field into compartments. Okay, so turns out this is a pretty famous place, this Wilmington oil field. It started in production in the early 1930s, and this place Signal Hill, which is right at the heart of the Wilmington oil field, in the day it was the most important oil field in the world. And today the Wilmington oil field is the third largest oil field in the U.S. And this particular place, I guess this is Signal Hill right here, remains one of the richest oil places per square foot of anywhere. And so you can see that this was these oil derricks were just embedded into the fabric of Los Angeles back in the day. These were, I don't know, I guess that looks like cars from the 40s. And here's another picture of Signal Hill from this era. Well, a lot of the oil has been recovered, but not all of it, and pumping continues. And here are some examples of some modern oil wells. So they found this place in the 1930s, and they went crazy with the drilling, put in a lot of wells, did a lot of pumping, got a lot of the oil out, but they continue to pump today, roughly 80 years later. So here's one of the things that happened. There are a lot of people that got rich, but there are also some problems. This is a plot of the oil that was produced on this axis as a function of time, starting here, and there's 1938. So the production, roughly linear up until there's 1954. And at this point, there's 880 million barrels of oil. Well, this other plot here is the subsidence, and on this axis we see the units of subsidence here in feet and here in meters. So by this point in the mid 1950s, after they'd gotten out 3/4 of a billion barrels, there had been 6 to 7 meters of subsidence. So the oil comes out, the pressure in the reservoir drops, and subsidence occurs. And so here's an example of some of the problems. This is an area that of the Long Beach area, and it's flooded. And the area is right down by the ocean, and so you drop the elevation by 6 or 7 meters, and you're going to have this kind of problem. And in addition to this, there are a variety of other more smaller scale problems, but very expensive nevertheless, with pipelines breaking. They had problems with bridges and wells that would get sheared off. So the subsidence ended up being quite a problem, quite costly. So they had a fairly clever solution. Here's a plot of the oil produced. Well, actually, this is the rate of oil produced. That's B/D barrels per day. And so starting in 1937, jumps up, and then for the next 20 years, it's in this range of production. And here's a plot of the subsidence rate. So 1947, the subsidence rate is, I think that's 48 centimeters per year. That looks like 61 centimeters per year. So it peaks. It's roughly half a centimeter or half a meter per year subsidence rate here, about 10 years after the oil field had been put into production. So what happened then was they realized this was a problem. There was a lot of oil there. People were getting rich. They wanted to continue to pump, but they couldn't really have this subsidence. So what they did was drilled some additional wells and started to inject water. And so this is a plot of the water injection. It's going up and continues to go up, at least up through the time of this plot. And what happens is that here we have some decline in production, so the subsidence rate is declining because of that. But now the production starts to pick up, but they're injecting water, so the water injection boosts the pressure in the formation, and that, you can see, reduces the subsidence rate. So it hasn't reversed the rate by this point. We're not getting net uplift, so there still is this much loss of elevation, but the rate of subsidence has essentially stopped as a result of this water injection, at least as of this paper. Okay, so this is an example of the poroelastic effect, where the fluid, in this case oil, and probably they're pumping a good bit of water as well, they pump it out, and that drops the pressure, and that induces deformation of this sand silt formation that holds the oil. So let's do a simulation. So the first cut here is going to be a very simplified geometry. We saw that the Wilmington Oil Field, the geometry of that is really fairly complicated if we wanted to include all of the details. There were faults, there were many different formations, but what I'm going to do is say, well, there's a well here in the center, and here this is 4,000 meters in radius, and this is an actually symmetric model. So this is roughly the size of the oil field. It's elongate, and this of course will be circular, but it's roughly the size. And the oil fields, as you can, or the oil wells, as you can see, they're very very closely spaced, and we're just having one well here, so that's not really very realistic. But nevertheless, this will allow us to have a fairly simple situation here, simple geometrically, and take a look at some of the processes that are going on. So there are two rectangles. This lower rectangle is the oil-bearing material or oil-bearing strata, and this is that unconformity. And so, for those of you who are not geologists, an unconformity is a place where there's been erosion. So at one point, this level here, at one point in the past, this level here was exposed at the surface, and there was erosion that took place. And then there were these sediments that were deposited on top. So these don't have oil in them, and they're going to be a confining unit. And this is the oil producing zone. And so to set this up, I have quite a few variables here. What I'm going to do is put a well here and pump from the well. So I need to define that pumping. And I also need to define the poroelastic properties in these two formations. So let me show you how I did that. I guess I'll come back to all these variables in a second. If we go to the poroelastic interface and the poroelastic material, what I've done here is used water as a material. So where we have to put in the pore fluid, I use the density and the dynamic viscosity of water. Now we could also put oil in, but I haven't done that for this example. And so for the formation, there are these parameters here that I need to define the formation. So the Young's modulus, and you can adjust the setting here. I think how it's first set up is the bulk modulus and shear modulus. So I usually use Young's modulus and Poisson's ratio. And what I did is put in these variable names for the Poisson's ratio, nu, and Young's modulus is usually designated with E. And these other terms as well, the permeability and porosity and the Bio-Willis coefficient, and here's the drain density. Okay, so what I'm doing, and I think this is something that you haven't seen, but I've got these two formations here, and they have different properties. So there are a couple of ways that we can handle that. One would be to go and put in another poroelastic material here, and we would have another entry like that, and we would fill in these blanks and have different properties. But the way I did it was I said that, well, these variables apply to the whole domain. And then up here in the definitions, I go here to reservoir properties. I have these 6 terms that are the properties of the reservoir. And these are the variable names that I've used down here. And these are the variables that I'm going to use to define these variable names. Okay, so under E, which I use right here, I assign E reservoir, and I'm going to do that in this subdomain here. And so what I've done is selected, I've gone here and said the geometric entity level is this domain, and then I selected that subdomain. Okay, so within that subdomain, the elastic modulus, the Young's modulus, will be this variable name. Okay, and I've done that for all of these. And if I go here to confining properties, I've selected this layer, the confining layer, and I have the same list of variable names here. These are the ones that I'm using down here, but I'm assigning different variables here to these variable names. Okay, so what I've done then up here in this list is define the values for these 6 names and these 6 names. All these 6 here are different from these 6 here. Okay, so come up here, here are the properties: the porosity of the reservoir and the confining unit, permeability of the reservoir and confining unit, and modulus, Poissons, and so on. Okay, so that's what's going on here. In this case, the porosity and the reservoir, this is a pretty thick reservoir, 1,500 meters, and so the body force of 1,500 meters ends up causing the stress to be quite a bit different at the bottom than at the top. That is affecting the porosity as well as the modulus. So what I've done is said that the porosity at the bottom is 0.25, and then it's a function of z, and I'm going to add on, basically what I do is z starts here at the bottom at 0, and so over this 1,500 meters I'm going to add on 0.15 to 2.25. So up at the top the porosity is 0.4, and then here the modulus is 3e to the 8, and by the time I get up to the top the modulus is going to be 2e to the 8 less. So the modulus here is greater than here. This is stiffer than that material, and that's how I'm this is how I'm doing it with this function here. Okay, and then the rest of these are just independent of depth. So the rest of this stuff is either is fairly obvious, except the pumping. I'm doing a few things here. Let me just show you how that's working. So this is the pumping rate, Q, and then I take Q and I assign Q to a variable that I call pumping rate. And this, I must say that this just kind of evolved out of developing this model. I don't really need to do this for clarity, but this is how it's evolved. So I have now a term called pumping rate, and if I come down here to well flow is ramp up times ramp down times pumping rate. Okay, so this is a step function that causes the pumping to increase over the first 5 seconds, and then ramp down causes it to decrease 20 years later. And then what's going to happen is I'm going to run this thing, and I'm going to decide that I want to inject water after 20 years, and just to mimic the procedure of injecting water. And so what I've got here is the well flow, and this is a volumetric flow rate. The pumping ramps down after 20 years, and then the injection ramps up. So here's the injection rate, and here's a step function that causes it to start up after 20 years, and then we'll inject at the injection rate. Right now I'm going to have the injection rate set to 0, so there will be no injection after. So we'll have 20 years of pumping, and then we'll stop. Okay, so for the boundary condition I need to have a flux. This is a volumetric rate, so I need to divide that rate by the cross-sectional area, and so I need to calculate the cross-sectional area. So here's the cross-sectional area. The screen length, which is 1,500 meters, we're going to assume that it's screened over the whole reservoir, and then this is the radius or the circumference of the well. So that's the area. So if I take the flow rate here and divide by the well area, then I have a volumetric flux, which is that term there, and that's what I'll use for the boundary conditions. Okay, so that I think is all of the definitions. This claystone, when I was developing this, I put in some beds of claystone. It's a low permeability material, but, and I think I've got it in there, yeah. So the permeability is 10,000 times smaller than the permeability of the aquifer or of the reservoir. But I'm not currently using that, so that's so we're going to skip over that. Okay, so let's take a look at the rest of the setup here. So axial symmetry, initial values. Um, yeah, this is essentially just the defaults. So the inflow boundary, this is the well, and what we're going to need to do is define all of the boundaries in terms of a hydraulic boundary condition and a mechanical boundary condition. So the hydraulic boundary condition here on this face is a flux boundary condition, and we use that term well flux that we calculated up in the definitions. And the mechanical boundaries around all of these boundaries here are roller boundaries. So they can move parallel to the boundary line but not perpendicular to it. And then I have two loads that are boundary conditions. At the surface, the load here is 0. The total stress is 0. And at the well face, the total stress in the R direction is equal to the pore fluid or the fluid pressure here of the injection well. Okay, that this kind of a condition for the well, that's really ignoring the supporting effect of the well casing. So this is the kind of condition that you would have for a well that's open. You could, if you had a very rigid well casing, then you could just make this boundary here a roller boundary. So that would be an option, and you can try doing both and see and compare them. Okay, so that's how this is set up, and let me see also sometimes when I've run this model, I've put the hydraulic head out here to 0. So this is what you would have if there was essentially some kind of source of fluid out here, or if this was past the influence of the well, and you wanted to allow fluid to flow into the well from, if the aquifer was essentially a large region and you didn't want to model it out here, but you wanted to have fluid flow from beyond this boundary in, then you could say it's a constant head. But in this case, I'm saying, well, there's a fault here, and the reservoir is truncated. So I'm going to say that it's a no flow, and I'm doing that just by using the default. So all of these conditions here are no flow. Okay, so the mesh, this is what I'm using for the mesh. And yeah, so it's closely spaced mesh here near the well. It gets bigger as you get away from the well. And then in the confining unit, I have more closely spaced mesh here because I'll be interested in measuring how the pressure changes as we go up into the confining unit. And I did that just by specifying the spacings along the edges here. And of course, there's a mapped mesh. Okay, so if I run this, I'm going to run it. I guess I'll just run it now. It's set up to run for 50 years. And what's happening is it's going to be pumped for 20 years, and then the pumping will stop. So here's what it looks like with the deformed coordinates. So we have subsidence. The color is the displacements. You can see that it's reaching the boundary here, and now we've stopped pumping, and the subsidence actually continues after you stop pumping. Now there's no pumping and everything's just kind of stable, and you can see we've got this subsidence that has occurred and is now uniform, and we can see why that has happened. Essentially, the reason it's happened is because this is no flow, so we pump the fluid out and drop the pressure, and there's no way for the fluid pressure to increase because there's no way to get more fluid back in here. So let's take a look at some of these responses. So here's the hydraulic head at let's see, this is sometime towards the end of pumping, and so low hydraulic head here, minus 400 meters of head, so quite a lot of drawdown. That's quite a lot, although that certainly is possible to have that much drawdown in this kind of a scenario. It would be less drawdown than this if there were many wells and they were spread out. But nevertheless, seems like it could be on this order. So the vertical displacement, what I did here was to set up a point here at the ground surface right by the well and a point at the top of the formation to look at the vertical displacements. So here they are at the ground surface. This is the subsidence as a function of time. We have 6 meters after 20 years, which is just about right. That's just about what was observed. And the top of the formation, it drops a little bit more. And then when we stop pumping, we have some uplift, and then it flattens out. So we get some of the subsidence back, but this is pretty much of a stable situation, and you can see here that's about 5 meters of subsidence that is permanent in this simulation. So we can also calculate the vertical displacement rate for the first 20 years. Here, what happens is it drops quickly at first. I've adjusted this so that it's in units of meters per year, and so it's quick at first, and then it levels out at between 0.2 and 0.3 meters per year. So it's a little bit less than we saw, but still it's the same ballpark. And then we get this big change when we stop pumping. Okay, so one of the causes of the damage was because there was vertical displacement. We saw the flooding, but horizontal displacement can also cause problems. This is the horizontal displacement at the ground surface as a function of distance from the well. And so right at the well, the displacement is essentially small, but as you get further away from the well, the displacement actually gets to be greater and greater. So the maximum displacement is this much at, I guess this is a particular time. So yeah, this is at the end actually. So so 20 years is about 6 times 10 to the 8th. Right about in there. Okay, so this is the displacement at about the time the pumping stopped, and so it's 0.4 meters and goes out about 1,500 meters, and then it diminishes, and it's negative, so it's negative R direction, so it's back towards the well. And so what this means is this point here is moving towards the well further, or towards the well by more than that point there. So from this point in towards the well, there's compression, there's contraction, and from this point outward, there's extension. This point is moving further towards the well than that point. Okay, and so that's something that causes problems. One of the things they had was a bridge in this area, and the bridge was having all kinds of difficulties because the bridge, I mean, say the bridge was 500 meters long, then one end would move this much, would move 0.3 meters, and the other end would move 0.2 meters. So there would be a tenth of a meter difference that the bridge would move. Well, that's probably not something that the bridge really liked very much. So this shows one example. The subsidence, the vertical displacement, is really pretty obvious, but there also is horizontal displacement associated with this, and it's because of the poroelastic deformation. Okay, so one thing that I want to show you that doesn't really matter too much with the Wilmington oil field, but it's an interesting and a fairly well-known effect, and it's called the Nordbergum effect. And this is a reversal in the water levels that occurs in confining units as a result of pumping. So what I did is to put some piezometers in the confining unit, and here they are. So here are these piezometers. One is right at the contact, and then they're at various distances away from the contact up into the confining unit. And so let's plot those. Okay, so this blue line is the piezometer that's in the formation, in the reservoir, and you can see the head drops by 150 meters after this time period, and then it comes back up after pumping stops. Okay, so that's fine. That's what we expect. The one that's, I think it's 50 meters up into the formation, it looks kind of the same, but it's a good bit less. And this one is kind of the same, but it's a good bit less, and same with this one. Okay, so fair enough. That's all. If we just look at this very quickly, then that seems reasonable. As we go into the formation, as we go into this low permeability confining unit, we would expect to have less of an effect of drawdown. Well, the Nordbergum effect, though, is up here, because you see what's happening is the heads here are dropping in this piezometer that's in the reservoir, but in the confining unit, the heads rise. All of these piezometers have the heads increasing as a function of time, and in this one, it increases for a long time. I mean, this is 20 years. So the heads have increased, and they're higher than the initial heads for almost 10 years. But eventually, what happens is the drawdown from the pumping in the reservoir propagates up through the confining unit and causes the piezometric level to drop. So what's going on here with this Nordbergum effect is that in the confining unit, as pumping goes on in the aquifer, that causes contraction, and in the confining unit there is also contraction, but because the permeability is low, the contraction occurs without the pressure response from the well reaching that point. And so when the contraction occurs, there's a volumetric strain that's a compressive volumetric strain, and when that happens, that causes the port pressure to go up, and so that's what's going on here. So this is quite a common thing. We see it in some cases in wells around here, and so if you're conducting a pumping test or involved with that kind of activity, and you see the water levels are going in the opposite direction of what you expect, then that's probably this Nordbergum effect. Let's see, I have some other piezometers that I've put in here. Let's see, these are at different radial distances away from the well, and they give a more typical effect where the water level is dropping, and here we're close to the well at this radial distance of 50, and then 200 and 500 meters away. Okay, so that's what's happening. This is for pumping, and then we shut the pumps off. Well, in fact, we would like to get this subsidence rate to diminish, and we'd like to get some of the subsidence to come back. So let's run this again, and what I'm going to do is pump for a while, like I did, but let's see, the pumping is done right up here. So ramp up and ramp down the pumping, but then I'm going to also use this injection rate, and I'm going to put the injection rate here. Come on. And I think I'll use 0.2. That ought to give. So the injection rate will be about half of the pumping rate during production. And we'll run that again. So really what's done is that pumping and injection are done simultaneously. Because we only have one well, we can't do that. We have to either pump out or pump in. So we're just simulating a more complicated situation with this fairly simplified case. So here we're pumping, and now we've stopped. Now we've started to inject again, and now the pressure is starting to increase for this injection. And here's the pressure is increasing. You can see the elevation is increasing. We're having doming going on, and so we've got some doming. We're starting to get back some of the subsidence. And I mean, if we were actually do this probably would be causing its own difficulties. So this particular design might not really be the greatest, but I think it'll illustrate this effect. So if we take a look again now at the vertical displacements, remember they went down, and then before they came up and leveled out. Now they're coming up and they're going back to the original displacement, or I guess this one is actually a little bit above it. And the piezometers, we see them rising, and instead of leveling off, the water level is rising. The vertical displacement rate, now it has this peak, and now it's actually a positive rate. So this is actually also then going to be a bit unrealistic, because in fact what's happened is the rate has diminished to roughly zero, but it hasn't started to uplift to my knowledge. Okay, and this is about the same, and the Nordbergum effect still happens here early on. And then actually we can see kind of another Nordbergum effect happening during the recovery, because you see right here where you would expect that the recovery, what happens with the recovery is that in the reservoir the fluid pressures reverse and start rising right away. But what's happening here is, instead of doing that, this guy is dropping, continuing to drop, and drop at an even faster rate. Okay, and that's because we're injecting here. That causes the formation to dilate, and that causes the confining unit to dilate, and that drops the pressure. Okay, so this kind of response right here is the Nordbergum effect during recovery.